Hi guys, just to recap, we've been talking about alcohols and making alcohols, or preparing alcohols as we say. We learned how to do that through substitution, SN1 and SN2. We also learned how to do that through electrophilic addition of a pi bond, so using Markovnikov and anti-Markovnikov addition. And so these are all reactions from first quarter OChem. And then I also showed you how to reduce carbonyl groups into alcohols using borohydride reagents, either sodium borohydride or lithium aluminum hydride. And the shortcut to that is thinking of the hydride as an H- ion, which technically it's not, but it's a nice easy way to figure out what's going on. And then we talked a little bit about dihydroxylation and how you can do that through KMNO4-OSO4 or through an epoxide and opening it up. Now we're going to talk about how to make an alcohol, not through just reduction, but also through alkylation. So up until now, you've only really learned one alkylation reaction, which is of a triple bond that's been a terminal alkyne deprotonated by NaNH2, and then you learned how to add this R group in an SN2-like reaction to get this alkyl group on here. Okay, so that's one way of making a carbon-carbon bond, and that's really important in chemistry, is to be able to connect molecules together, connect pieces of alkyl chains together to make larger and larger molecules. So along those lines, I'm going to show you another way to do that. That's with something called a Grigard reagent. This is named after Victor Grigard, a French chemist. And so to illustrate, I'm going to show you this reagent RMGX. So this is called a magnesium, some alkyl magnesium halide reagent. That's what we call the Grigard reagent. And this Grigard reagent has a magnesium in it, and that's really unusual to see metals. But we've used metals a few times as ions, like counter ions, like sodium ion and lithium ion and potassium ion. We've seen like NaBH4, LiAlH4, KOTBU, but they're counter ions. Here we're talking about magnesium, sort of like this. An R group is attached to magnesium, which is attached to halogen ion. So this in this format, it's not quite a salt yet, but you can think of it like some kind of a ionic compound. So the metals are usually electropositive. So I put a partial positive on this part, and a partial, that will cause this to have a partial negative. So electropositive elements push electrons away from them. This is electronegative, so pull those electrons over to itself. So this is pushing away, and that's causing that to be more negatively charged. So in a sense, this can be thought of as an R minus and an MgX plus, if you think of it in an ionic sense. But it is more covalent in nature, but it helps to think of it as an ionic interaction, because then I can think of this guy as being nucleophilic. This is my negative, this is my positive, and this is going to come and attack this positive here. All right, so negative goes to positive, then that's going to push this up, and that's how I'm going to get a reduction here, but I'm going to get an R group added here. So this is alkylation. Now notice this is different from what we did before, which was we used a hydride reagent like NaBH4 followed by water. And I know Klein puts methanol in there, but I like to just have a water step separate, because this could react with that. So this I think of as hydride. Let's put it in red, just like our R group is in red. So instead of this R group, I have this hydrogen, which I think of as this. And this comes in and attacks. See how similar this mechanism is to the Grigard reactions? It's basically the same thing, except this is with an H. So you're just going to get the H here. So you just have reduction by itself here, whereas here you have alkylation. So often you can just use the Grigard reagent, but you might see reactions where you have to make that first. So how do we make the Grigard reagent? Well, you are going to do a lab on this if you haven't already. You take an alkyl halide, Rx, and you add magnesium metal to that. And then they react together, and the magnesium inserts itself between the alkyl group and the alkyl and the halogen. So no need for electron pushing mechanism here. You can just show this as a step, and sometimes they put the solvent. It's usually diethyl ether. Now it's really important that the solvent is aprotic and that we don't have any traces of water around, and that's because the Grigard reagent can react with water. Remember, the R group is our negatively charged ions, very strong base actually. And so if we have water around or some kind of protic solvent, this is going to grab the protic solvent before we can even react it with our carbonyl group, the molecule that we want to react it with. It'll just go for the solvent. And when that happens, you're going to end up with an alkane. Nobody wants that, right? So, well, maybe if you do want an alkane, you just need a source of protons. And then this solution will be basic because of the hydroxide left over. So in any case, yeah, you don't usually want to go for that. And then this MgX part usually is the counter ion to this OH. So this will be the positive part. So sometimes you see this written together as MgXOH. Okay, so now let's do an example, and why don't you take a moment and follow the mechanism, assign the dipole to this Grigard reagent, and then show me how it attacks the carbonyl group. And then also show me the water workup step. Go ahead and give that a try. All right, guys, so what I have is the methyl group attacking here, sort of breaking this bond and attacking the carbonyl at the partial positive part of the carbonyl, which is the carbon. Then the electrons flow up to the oxygen, and I have a negatively charged oxygen now, 3 lone pairs. All right, then I have the oxygen needing to get neutralized, hence the water workup step, or sometimes dilute acid is used. And then I get this compound here. Now this problem asks us to use a Grigard reaction to prepare these compounds, meaning to form these compounds. So you can use any kind of Grigard reagent. They don't specify how to make this, but they just want you to demonstrate using a Grigard reaction. So for me, I'm thinking this OH came from a carbonyl group, so I need to have a carbonyl here, and so probably came from some kind of carbonyl group, and then I can decide which R group that I want to add. So maybe if I had either a methyl group come and attack the carbonyl, or I could have this propyl group come and attack the carbonyl. In fact, I could do two Grigard reactions, but it would be a little bit more complicated than that. But let's try just something really simple. Let's just say the methyl group here on the end got added on as an R group. So that means then I'll have the rest of this molecule. So this will be butanal, 1, 2, 3, 4, butanal. And then I need this methyl group on the end to come and attack. So let's say that I had CH3 MgBr. So this came and attacked, and then I did water workup as a second step. So my reaction is going to be 1 CH3 MgBr, 2 H2O or H3O plus dilute is fine. Okay, so basically just think of 2 ways you can do this. Another way I could have done this is to have, I think you guys can see, I could have that. So I have this piece to start with as a carbonyl, which is like that. And then I have CH2, CH3 propyl group come and attack there. So either way I'm going to get this compound. There's not a lot of steric hindrance either way, so I think I'm okay. So propyl group is linear, so that's fine. If there was a lot of steric hindrance, though, you'd have to wonder about how you're sort of setting it up to be slow then. So try to avoid steric hindrance when you do these. And so this one will have to be the MgBr. So this is propyl MgBr. This comes from propyl MgBr. Okay. All right, so go ahead and give some of these a try and see what your possibilities are. All right, guys, so we're back, and mainly I'm just looking at what are the pieces I could add together. Here, I could either add the propyl group to 3-carbon ketone, or I could just add a methyl group to it. So that's what I did. It doesn't matter, but I added the methyl group here, and so now I have 2 methyl groups, and then water workup after all these steps. This one only has 1 R group, so I have to add that. So I started with what's called formaldehyde, which I'm sure you've heard of before, and then water workup after that to get this H on there. Here I just decided to keep this part, and then I would add an ethyl group as the Grigard reagent, and then water workup again. So along the lines of Grigard reactions, it's pretty simple then. It's like a hydride addition or reduction reaction. I have molecules sometimes that aren't compatible with Grigard. Like I said, Grigard is pretty basic. This R group is a very strong base because think back to our alkanes. This alkane pKa is really high, like about 50. This is a very weak acid, which means its base is very strong. So these are conjugate bases of alkanes. They really want an H. So if you think about it, if there's an acidic H, it will grab that before it attacks the carbonyl. And if you see any acidic H's on here, I think we all see one here, then it's going to grab that H instead of attacking the carbonyl. So this is going to come in and do this instead of the kind of reaction that we desired, which was to attack the carbonyl. All right, so in this kind of situation, this is not going to go the way that I had planned if I wanted to attack the carbonyl. So I'm going to end up with conjugate base, which I could have just used NaOH if I wanted to do that, right? Why use an expensive Grigard reagent if I'm just going to get an H out of this? So it's not really the best thing to do here. All right, same thing here. Do you guys see an acidic H here? This is an alcohol group right here, and that H is pretty acidic as well. Considering that this is a very strong base, it looks at that H as pretty acidic. So what I'm going to do is grab that instead, and we'll make our alkane again, which I don't want, right? So anyway, what this is just to demonstrate what is usually undesirable. Usually I don't want to do these reactions. So I need to think of a creative way of getting around this issue because maybe I do need this to react at the carbonyl. How can I force it to do that? So now we have this idea of a protecting group. A protecting group does that. It's a group that protects that functional group from reacting undesirably to allow other places in the molecule to react. And then that protecting group can be changed back into what it was before so that you still have that group. So here's how the basic idea works. And I put he because acid base, it's basic. Grignards are basic. Okay. Anyways, protect the OH group. So OH group reacts. We don't want it to react with our Grigard. Otherwise, we're going to throw away our Grigard, basically. So what we want to do instead is we want to make that OH group protected so the Grigard doesn't see it. The Grigard goes for the more reactive part right here. So let's say that our Grigard goes for the other center that's reactive, which is our partial positive here, and displaces that. So we're going to get an R group here. Now you might wonder where did the OH come from? So I think there were some other reactions here, or maybe there was a carbonyl group eventually somewhere in a multi-step reaction that the Grigard added to. But in any case, once you react that, then you can remove the protecting group and you get this OH back. So what is this protecting group that's allowing us to ignore that hydroxyl when we want to and then bring it back when we want to. So the protecting group that we're using right now is of a OH group, so hydroxyl protecting group, and it's called Trimethylsilyl Chloride. So trimethylsilyl chloride looks like this. It's silicon with 3 methyl groups and a chlorine attached to it. And what's going to happen here is the O is going to displace the chlorine, and we're going to get a TMS group, trimethylsilyl group on the O. And then the solvent they're using here is triethylamine, and what that does is it gives me the basicity I need to pull this off to then attack here and release there. So this is going to be an OTMS group. This is my protecting group. So now what I do is I use Mg to turn this into a Grigard reagent. So after step 1, this group is going to become MgBr here, and then I'm going to have this OTMS. So look at what they're doing here. They're reversing the Grigard from what you're used to. You're used to seeing the RMgX here, but now they're actually making it here and giving you the carbonyl group as a reagent instead of the other way around. So this is good for you to experience that both ways. So once you make the magnesium insert between there, you have the Grigard reagent here after step 1, and then this Grigard reagent is going to react with the carbonyl group. So here's my positive part, here's my negative part, this carbon right here. So that's going to come and attack here. And it might be better actually to show this bond breaking to make a new bond there. So the electrons sort of bounce from here to this carbon, and that carbon makes a bond there. So what we have is this OTMS group still on there. It's just following around, it's just going with the flow. And then this carbon here is right here. And we have the double bond O turning into an O minus. And the water workup is how we get that H on there, and we have the 2 R groups from the carbonyl containing compound right here. So that's how we alkylated it. Now, let's say that we don't want TMS anymore. We want an alcohol. We can remove that. Here's how we remove that protecting group. We use something called tetrabutylammonium fluoride, TBAF, or you can just use H3O+. And usually what happens is this protecting group can fall off, so you can have a fluoride ion here, attack here, displace that O group, which can then get protonated by water in solution. So that source of fluoride ion is what this TBAF is for. Or you can just use H3O+ if you want. That's very commonly used to remove protecting groups, certain ones. This one is acid sensitive, so you can remove it with acid. So using the ideas that you've learned so far, which are Grigard reaction and protecting groups, see if you can do these transformations. So for this molecule turning into this one, you see that the Br was replaced by this group here. So see if you can think of a Grigard reaction for that, but we need a protecting group because of the OH that's present. Same idea here. We're adding an alkyl group here, right here. We're adding this whole big thing here. So see if you can think of a series of reactions and write them over the arrow. Alright guys, we're back. First we need to take care of this OH group. I don't want to have Grigard react with this H, so I've got to protect it first. So I'm going to put a TMS group on here with TMSCl. Once I do that, then I'm going to have a magnesium enter here and make my Grigard reagent. React it with 1,2,3 carbon ketone called acetone, and then I can protonate that and get rid of my TMS group with some acid. Same thing here, but now I have this bigger molecule to add, and it's got an OH group as well. So I need to have a TMS group on here. So I might want to start with this molecule here, and then use TMSCl on this molecule to protect that OH group here. And then I can remove that and remove this and protecting group and protonate here by using acid. All right, so this is going to take some practice to get used to protecting groups, but remember to keep that in mind when you have a reactant that has an acidic hydrogen that might be prone for the Grigard to attack. So you want to protect it first.